Hi, hello, I am Jacqueline, and this is week three's biochemistry presentation. So the prompt is, hemoglobin is a protein which binds oxygen in the lungs and releases it in the capillaries. Interestingly, your body controls this intake and drop-off of oxygen by having different pHs at the two locations. So a heme group is non-planar when the oxygen is not bound to it. The iron atom is out of the plane of the porphyrin ring towards the histidine residue. This is the non-planar configuration of deoxygenated hemoglobin that is called the dome shape, as you can see on the bottom over here. However, when the oxygen binds to heme, it gets planar configuration where iron lies in the plane of the porphyrin ring, and the binding of the oxygen molecule at the 6th coordination site of the iron substantially rearranges the electrons within the iron so that the ion becomes effectively smaller, which allows it to move into the plane of the porphyrin. This change has taken place in electronic structure and magnetic properties of hemoglobin, which are the basis for functional magnetic resonance imaging, which is MRIs. So the free heme is not favored for oxygen transport. So globin in hemoglobin has been used to stabilize the heme oxygen complex, and it can act as an effective carrier of oxygen. Sorry. The quaternary structure of hemoglobin is markedly changed on binding oxygen. Its 3D structure includes a pair of identical alpha-beta dimers that associate and form tetramers. In the deoxy state, the dimers are linked by extensive surface and heme groups, as well as separated corresponding to the T state. On oxygenation, iron moves and brings iron-associated histidine towards the porphyrin. Therefore, the histidine-containing alpha helix is altered. And then it's the R state. The binding of oxygen is cooperative. A decrease in the pH shifts the standard curve towards the right, and this occurs because of a greater at greater hydrogen ion concentration, various amino acid residues such as histidine stabilizes the deoxyhemoglobin in the T state. And then the T state has a lower affinity for oxygen than the R state. So with increased acidity, the hemoglobin binds less oxygen for a given PO2 and more H plus hydrogen. This is known as the Bohr effect. At high pressure, it exists in lungs and gills, and the HB is a good O2 binder. At low pressure, muscle and tissue is a poor O2 binder. At low pressure, HB passes the O2 myoglobin. The need for oxygen is greatest in tissue, where the oxygen is consumed rapidly with the production of carbon dioxide. The CO2 lowers the pH, causing the hemoglobin to release more oxygen to the myoglobin. Again, this pH sensitivity is called the Bohr's effect, and the hemoglobin curve is sigmoidal in nature. So as I mentioned before, carbon dioxide is acidic in nature. So when it interacts with water, the pH of the capillaries decreases. And then at high pressure, at And then oxygen is transported from the lungs, where its partial pressure is relatively higher. It's around 100 torr, to the tissues where it is low, where it's around 20 torr. Therefore, in lungs, all hemoglobin is nearly saturated with oxygen. And when it moves to tissues, the saturation drops. And then in the lungs, the hemoglobin saturated with oxygen is approximately 98% of the oxygen binding sites are occupied. And on the other hand, in tissues, the saturation level drops to around 32%. Thank you.